with the shell model and discuss the nuclear shell model. But then before we start with discussing nuclear shell model, we need to understand that why shell model is important and why models like the liquid drop model did not work well. Okay, so there are certain aspects which could not be explained by the liquid drop model, and that is what we are going to see. But then, as I always believe that without straight, I don't want to jump into the topic of what potential is used in understanding a shell model and so on, go into the technical thing, mathematical calculation. First, let's form a good base so that we understand that why we need shell model. So, if you consider an atomic model and if you consider something like a gas which is inert in nature, in general, we do know that the shells are complete for these inert gases. So I'm considering the atomic model here, and we are trying to draw an analogy with the nuclear model. Okay, what happens inside the nucleus and what happens in an atom, somewhere they do meet. Okay, they are having some similarities. So if you consider something like an inert gas which actually does not react with, let's say, oxygen in the atmosphere or the atmosphere itself, any gases present around it, okay, until and unless you are actually putting it into a different physical condition altogether, high pressure, temperature and so on. So in general it does not react, so it is called an inert gas, and that happens because the outermost shell is complete. So if we are considering something which has got 8 electrons, which is filling up all the outer shells and no more electrons can get into that shell, that is basically called the filled shell. So we basically call them the valence electron. So what happens is if we try to add an additional electron, we will see that a new shell will start. Okay. So if you actually want to start an additional electron, or if we want to add an additional electron, one electron, we are adding a new shell will actually start. So this is how the inert gases works. Moreover, for the atomic model, we know that a lot of property, okay, has been decided by the valence electrons. Okay, the valence electron decides a lot of property of any element, number of electron present in the outermost shell. Inert being one of the features, okay, which is decided by the valence electron. If the valence shell is full, we know it is inert. So whenever we consider gases like helium, argon, neon and so on, okay, they do have a very low chemical reactivity. They don't react readily with any of the gases which is present around it because they are inert. Okay? And because of this, this has also got a lot of application. Now this chemical property actually depends on the shell structure, how the electrons are arranged and so on. Okay, so which shell we are talking about and so on. So this is an important part, and what happens is if it is a closed shell, that means the electrons are tightly bound to the system, and if you actually want to pull the electron, okay, you want to take out an electron from that particular shell, it is a bit difficult because you need to put a lot of energy, okay, and that energy that we put in is called the ionization energy. So if it is a closed shell, ionization energy will be more. Okay, if it is an open or not open, sorry, if it's a shell which is not closed, there are probability that more electrons can come and join in that shell. We can have a lesser ionization energy for that particular system. This is how you talk about the hydrogen atom, and you have that relation of E is equal to minus 13.6 by n square and so on. Okay, so these all deals with ionization energy. So this is the atomic physics idea or the atomic model idea that we already have. How do we do it in nucleus? In the nucleus, a similar thing happens for protons and neutrons. So whenever we basically have a proton or a neutron and not the electron, and we divide it in energy level states, okay, the energy level is divided, the quantization of energy or the energy gap that happens between two energy level will be different. So for an atomic structure, the energy levels will be different, the range will be different, okay, it will be spread over a larger range, okay. But then if you consider proton and neutron, this range will again be different. So we have to understand that yes, there is similarity in terms of the formation of energy levels, but then the values doesn't remain same, okay, because obviously proton, neutron all together has different property, carry different energy and so on. So whatever we did till now in the first unit, apart in second unit, we actually also saw about binding energy per nucleon. Okay, so binding energy per nucleon, you can measure it, okay, and you can actually get that graph, and then you do a binding energy per nucleon which is calculated. And how do we do the calculation? Well, till now we have seen that the calculation can be done from the semi-empirical mass formula. So we do the binding energy calculation using the semi-empirical mass formula, and there we actually saw there are a lot of terms which actually can be explained, okay, with the help of quantum mechanics, with the help of basic idea of electrostatics like the Coulomb term or the asymmetry term and so on. Okay. But then the semi-empirical mass formula is actually derived or actually idealized from the liquid drop model. So you know that if you have a very heavy nucleus, it wants to break into two. It's not that it will happen spontaneously, okay, it does happen very fast, but then there is a very regular process in it. And if you have studied liquid drop model before, which is not a very like topic which might not be taught, might have been taught even in your degree also. So if you have basically a liquid drop and then it slowly breaks, okay, you apply some energy and then this becomes in this shape, and then it becomes totally different and so on, okay. So then it separates out, and in between there are intermediate stages. So this is how a liquid drop model works, and based on this we actually have the semi empirical mass formula, okay, and that will actually give you a calculated result. But what we have seen in the graph, that whatever is the calculated result doesn't match with the measured result at each and every point, okay, because if you look into the binding energy curve, there are certain points at which there is a very sharp peak, for example helium, lithium, okay, and so on. So what happens is that the binding energy per nucleon is more there, and this is what is being observed, okay, measured. But then as per calculation it is not seen. What does it mean? It means that the semi-empirical mass formula cannot explain it, okay. That means the liquid drop model doesn't explain everything, okay, when it comes to explaining binding energy per nucleon curve and so on. So what do we see here is, this is not the entire range. I think we have already seen the entire range, and that's something you can easily remember. But then what happens here is that we see that range at certain points there is a peak. There is a peak. So there is a peak here, there is a peak here, there is a peak here, and I've just illustrated this, okay. There's a peak here, and you can see the value here, and then this is n is 28, z is 28, n is 50, n is 82, z is 50, n is 126, z is 82. So these values which we have are basically called magic numbers, okay. These are called magic numbers. This is not exhaustive, there are more magic numbers. I'll show you the list in the next slide. But then what happens is, if the shell are actually large, it basically deviates from the liquid drop model. What does it mean? That if you are considering a lesser number of mass, okay, atomic number, this is the A value or the atomic number is lesser, okay, it's fine. It more or less liquid drop model can tackle it and give a good understanding. But when we go to larger and larger atomic number, the number of protons, the number of neutrons keeps on increasing, we actually cannot use liquid drop model because it doesn't explain it fully. So then we need to go into a different model, which is the shell model. So liquid drop model came well before the shell model was seen. But then since it could not explain, then scientists tried to understand what exactly is happening, and then quantum mechanics started developing and so on. And then the shell model was more or less validated. Okay. And what we do is that we see that the measured and the calculated value of binding energy curve will actually differ. And this is what we are going to see. But the difference that we are going to see from the shell model is in terms of explaining the magic numbers. That means the peak, okay, that happens. So these values, I think these values is something which we should all remember. 2, 8, 20, 28, 50, 82 and 126, okay. So how many values are there? There you can see 4 plus 3, 7. So these values are basically called the magic numbers. So what does it signify? It signifies that within the nucleus, you either have the neutron or the proton having these many numbers, okay. So these many number of neutron is there, or these many number of proton is there. That is called magic number. But then there are cases, let's say for helium, there is 2 proton and 2 neutron. So both of them belong to this category of magic numbers. So these are called double magic numbers or doubly magic numbers. Okay. So these are double magic number elements. Okay. And there are elements which are single magic numbers also. Okay. So what happens is that if we basically have an element which in which the number of proton or neutron bears a magic number value, or both of them bears a magic number value, the number of isotopes that exists for that particular element is also more. Okay, so these are called the magic numbers. Beyond these numbers, the nuclei is not stable. Okay, so this is important. So if you go beyond this, the nuclei becomes unstable in nature. So what happens is if there are more neutrons, and more protons coming into picture, anyway it's becoming more and more unstable. But then for certain higher neutrons and protons, it's still stable, and it is something which is belonging to this category of magic numbers. So we can look into that element later. But then, just as in the case of atoms, the energy shell will close at these values of neutron or proton or both. So if you consider an atomic model, you know that the valence electron is full or the valence shell is full. Then if any more is added, any more electron is added, it takes up a new shell. So similarly in case of nucleus also, the neutron and the proton, if it has this magic number values, it will close at that particular shell. Okay. So if there are any gaps in the energy level, then what happens is they actually form different shell altogether. We can actually plot it. We will see it later. Okay, we are going to see it in the next class. Even today also, we are going to see one part of it. If there are gaps in the energy level, that will actually form one shell. But then there are some energy levels which are grouped. That means on the energy scale, they are very, very close to each other. Okay, then these shells structure will arise. Okay, this shell structure will arise. Okay, so before I go to the next part, I think all of us know about this valence band and conduction band. So you do have a semiconductor idea, and you know that there is a valence band and a conduction band, and then there is a band gap which we usually refer to as EG. But you know that this valence band and conduction band is actually an idea to explain conductivity, or whether it's an insulator, or whether it's a metal, and so on. Okay. So in general what happens is that it is not that this will basically be a continuous band. Okay, it's like the energy levels are so close to each other, the energy levels are so close to each other that they basically are forming a very closed group. So if they are basically forming a very closed group, they will actually comprise of a band. So this will be like valence band. And then there is splitting of energy level, because of which there is a gap. There is a very good understanding of this in semiconductor chapter. There is a gap which arises, okay, because of which if there is any electron in this energy state, cannot jump to the upper energy state. Okay, if it's an insulator, if it is slightly lesser, it can still jump with application of energy, and that is semiconductor. So there will be another group of energy level which will be formed, which is basically called the conduction band. Okay, so this is how valence band and conduction band works. Okay, so here also similarly, in a similar way, we do have energy levels which are very close to each other, and they are actually belonging to one group. Okay, so this is what we mean by energy levels are grouped. Okay, so if we look into this, we are now just going to concentrate it in terms of protons and neutrons. We are not going to look into it from atomic point of view. Okay, we are just going to look into it from a nucleus point of view. So let's assume that for each proton and neutron, the nucleus will provide some potential. Now this is true, right? It will definitely have some potential, because you see proton is charged, it will have that electrostatic potential, and even neutron will actually contribute to the potential because it does have some kind of mass. Okay, and potential is something which is also mass dependent. Okay, so these ideas are there, and then if you basically consider your quantum mechanics, and consider that a neutron or a proton in this case is trapped within the nucleus, you can use the idea of square well potential, and try to understand that how much energy is needed to overcome the potential within the nucleus. So that is where we use actually quantum mechanics. We are not going to derive a lot of things here. Okay, but then what we do usually, what is the approach? The approach is solve energy level for these potential. Okay, So you have already done quantum mechanics first part, and then you have studied it before. Now also you are going on with quantum mechanics second part. But then the basic thing is that we are trying to solve that potential problem. Okay. But then if you look into the application, it does have its application in atomic physics, nuclear physics, and so on. So I think this is one of the good applications that you see. Okay. And then you know that okay, you need quantum mechanics here, very important. So again, I'd like to repeat, you have a neutron or a proton trapped within the nucleon, and you want to understand or you want to realize that how much energy does it need to overcome the potential. Okay. So for that, I think one of the better ideas is to consider the square well potential. Okay. So there we can say that this is trapped within the nuclei and it can actually exit or escape the nuclei. Okay. If we are applying this much of energy. So you can use that relation of E is equal to n square h square pi square by 2 ms square. Okay, hopefully I'm saying that correct. But then the question is, this square well potential that I'm talking about is not the only kind of potential. There are different kinds of potential. The harmonic oscillator problem is there and so on. Okay, so the question is, what kind of potential do we start with? Okay, that is the question. Okay, try to understand this. The essence of this particular lecture is to understand that why we are uh, using shell model and what kind of potential can we use to understand shell model. Okay, or what kind of potential we can understand, we can use so that we can actually relate it with the nucleus more realistically. Okay, it will be more realistic in nature. Okay, not too many assumptions here. So then the question is, what kind of potential do we need? Okay, so as from quantum mechanics, the very first potential that we know is nothing but the infinite square well potential. Okay, and this is the potential function that we already know. So I'll put everything here. So you basically have the neutron trapped within this. Okay, okay, and then it is an infinite square well potential. So if I say that Vr is infinity, that means it doesn't have sufficient energy to actually escape the nuclei, right? Because the potential is infinite. So that means that the walls are too deep, and that is the reason we call it as infinite. Okay, infinite means it is so deep that even if we apply some energy, the potential is infinite, so high that the neutron or the proton probably can't escape the nuclei. Okay, this is exactly what we mean by infinite square well potential. Okay, so it basically depends on R naught. So what is the uh, distance within which the neutron can move? So if you consider a nuclei, typically it will be 1 Fermi. Okay, 1 Fermi, 1.2 Fermi. As I said the other day, it won't go beyond 2 Fermi. Okay, most of the times. So it is 10 to the power minus 15 meter. It is trapped within this range. Okay, so we have the value now. So if you've learned quantum mechanics superficially, then sometimes you're confused that what should be the value, but depends on what kind of problem you're considering. But if you have studied in depth, okay, you have considered it not for exam but for understanding purpose, you already know that what will be the different values of R naught for different kinds of problems that you consider. So in this case, might be we can take it to be 10 to the power minus 15 meter. Okay, and this potential actually does not depend on theta or phi. So it does not depend on those spherical polar coordinate, but it depends on r. Okay, so that is important, and since it depends on r, we know it is basically called a central potential. So we already know the definition of central potential, that it depends on the distance. Okay, from the center of the nuclei, okay, in this case. But then the wave function that we have, that necessarily is not independent of theta or phi. Okay, the wave function will have a spherical form. Okay, it will come in and then it will get scattered and so on. So that means the wave function cannot be considered, the wave function associated with this potential. Okay, so you know the neutron and proton will have a wave function associated with it. So that wave function cannot be the a pure dependent on r. Okay, it will be dependent on theta and phi. I think this is something which you have already seen when we talked about the scattering problem. So this relation will be nothing but in terms of r, theta and phi, and then here also comes in the mathematical physics, as we already know that YLM is nothing but spherical harmonics. But don't be scared, we are not going to derive anything here. We are going to try to understand this qualitatively, okay, not quantitatively, because this is not the aim. The aim is to solve a different potential altogether. So even if I skip this, it's perfectly fine, but I don't want to skip because I want to tell you why this potential does not work. Okay. So then the wave function will depend on theta and phi. You can just remember this, okay? Even if you don't write down this relation during exam, is perfectly fine. I'm not going to deduct your marks, okay? So YLM is basically called the spherical harmonics. And if you want to solve this spherical harmonics, you know from mathematical physics that you have to use Bessel function, right? So this Bessel function will actually give you a solution which needs to be solved. And after you do all the solutions and solve everything, okay, which even I have not done, you don't ask me that, okay, I don't know right now. If you actually do all the solutions and all, you can actually find out what are the possible energy levels, okay. And then if you actually plot it, if you plot the energy level and if you consider the quantum mechanics part, that means the quantum states, that means no two particle having the same quantum state, so having the same quantum numbers can occupy the same state, right, energy state. So this is what is quantum state is all about. So then if you look into these different orbits, okay, or different shells, in this case we can call it as shell because this is what we are coming across with the definition. We see that if we solve this for the energy level, in the ground state, 1s state, we will be having a maximum of 2, okay, 2 neutrons or 2 protons, okay. And on the other hand, if we go to the p level, the value would be 6, and then so on. So we can do the calculation. We are not doing the calculation here because we are going to do the calculation for the next few problems, okay, and you will understand how this is done. It's not going to be very difficult. So this is going to be 10, 2, and so on, okay. So let's look into this now. So at the ground state, we have the number as 2. So 2 is a magic number, okay. So it explains this. In the next energy level, it is 8. How? 2 at the ground state and 6 at the next energy level. So we can add them up. There is a cumulative addition. So it is 8. Okay. The shell is closed. So second magic number explained. What happens in the third shell? In the third shell, we have it as 10 and 2. Now these 10 and 2 combine together because they are very close to each other, okay. When we look into the harmonic oscillator problem, we will look into it more closely, but here we see that this 10 and 2 will combine together and it will give you 12. So add them up, 10, 12, 18, 20. So we have got 20, which is the third magic number. But then if you actually solve for E and put for the next value, you will see that in the F state, they are basically 14 number of neutrons or protons, okay. So that means, see, we can actually solve it for separately. One energy level for neutron, one energy level for proton. But I am just considering it in general, okay. We can consider it either to be number of neutron or number of proton. So if you go to the next state, it is 14, but then it is 34 here. But then the next magic number was 28. So this is not explained, okay. So as you go to higher orders, you see that the magic numbers are not anymore there. So you have the explanation for the magic numbers only up to the third value. That means for low atomic number. If we go for higher atomic number where there are more number of neutrons and protons, the magic number is not explained, okay. So what we can say that 34 is basically not a magic number as suggested by experiment, okay. So you know it magically gives a peak, okay. So this 34 doesn't give that peak. It gives at a peak at 28, okay, and it was seen that it is actually nothing but the number of proton neutrons are 28. So doesn't give that, so that means it's not a magic number. So we cannot consider this model, okay, or this potential for understanding the occurrence of magic number. So this potential is not valid, okay. Where do we get this energy level 1p, 1s, 1d and so on? Because we are studying shell model. So we are studying the quantum mechanics now in nuclear physics. So this is based on the shell model, okay. Because of the shell model only we can consider this in terms of energy level, not the liquid drop model. Liquid drop model is very much theoretical. It has got a lot of explanation but not much quantitative explanation. But here we do have a lot of quantitative explanation, and as you understand, if we involve more maths into our calculation, we try to understand it better, okay. But then we have to remember that these energy levels which comes because of the shell model is not as per the atomic energy scale, okay. So it is not as per the atomic or the molecular level, it is a different energy level altogether, and then closed levels are counted together. So if you consider this d energy state, okay, we have got 10 and 2 which are actually close together. Not great drawing skills of mine, as you know, that's why you cannot differentiate it, but don't consider this, every diagram is not up to the scale here, okay. If you look here also, you see that these energy levels are closer. So energy level close together are counted together. Okay. So then what is our conclusion for the square well potential? Okay. The conclusion for square well potential is that if we solve this square well potential, the experimental values of magic numbers are not shown and hence can't be considered in the shell model. Okay, we cannot really explain the occurrence of magic numbers in shell model if we use the square well potential, and that is the conclusion. Okay, so then what is our aim? Our aim is to shift to the next uh, concept. Okay, and that is nothing but the harmonic oscillator problem. So this is a kind of infinite potential again. Okay, so we basically have an harmonic oscillator, and then if we actually write down the relation, what we do is we basically just consider the potential function for the harmonic oscillator and then check if it tallies with the experimental result for the magic numbers. So we will going to observe that this also does not agree with it. Okay, so I just want to give you some food for thought for the next class. Okay, I thought of doing this today, but then I thought, okay, I have a class at 11:30, so probably I would continue, but then I don't want to leave it halfway also. But then I will still tell you to recall this, because I think this is something which you have already done in your quantum mechanics. And if you consider a single particle potential, then after doing all your calculations and all, the potential associated with it is half m omega square r square, right? So that is the potential associated with the harmonic oscillator, and then the wave function will have a similar form, and you know the result of energy which we can be deriving from the wave function will actually depend on what kind of potential we have considered. Okay, wave function is a very general statement, right? So when we plug in the particular energy value, we plug in the particular potential value, then only we can actually get the final output from the wave function. So if we consider this, what we have is the wave function, and then plug in the harmonic oscillator potential, and then actually you find out the result. So this is the form of the wave function that we have. Okay, and once we solve this, we get the energy. Okay.